Hi, William.
Hello, hello.
Oh, it's so good to see you,
Good to
William.
see
Are
you
we
too.
good? Oh, I forgot to give you a background. Do you mind if I do that really fast? Is that
Yeah,
okay?
go
I have
for
like
it.
a really pretty. Let me give you my gorgeous background. So this way all of the videos are uniform.
Sure.
William, it's such a long time. I haven't seen you in so long. I miss you.
It's been a bit.
I, it's been a long time.
I still hope I'm still down to make a trip out to New York for a seminar. I
I
think it'd
know.
be fun.
Well, yeah, totally. I just emailed you the background. I'm also going to send it
All
to
right.
your phone.
Here, send it. My email is a better way to go. Hold on. All right, there's you. So wait for it to pop.
Hold on, I'm
Got
sending
it?
you.
All
You'll
right.
get, it's only 20, it's like 10, 20 kids, but you know what? It's like,
That's fine.
this is a good video, and then I'll Venmo, I'll take care of everything after, but this is a good
Save the
opportunity.
details. Yeah, no, I'm happy to just do it. It's fine. It's nice to
Good.
have a
I'm letting
toe back in the
everyone,
water.
I know. Hi, everyone. Get everybody. We are so lucky that William is doing this because, hold on, I'm going to spotlight myself. I just want to let you guys know you're so lucky that William is doing this because he's doing this all the way from California. Do you believe it? Hold on just a moment, William. Okay, I'm doing a security setting. Hold on.
Sure. There we are, unnamed. Ah, there we go.
So what am I doing? I'm spotlighting me. Hold on. Back to me. Hello, everyone. Ugh. I'm really glad that we're doing the Zoom. Who wants to see my cute little Goldie before we get started? Who wants to see a cute little dog? Ready? Wait. Are you ready? I have to get rid of my background for you to see my dog. Hold on. Nope, can't figure that out. Sorry, guys. This is the best I can do with a dog. Whoops. Goldie does not have amazing face recognition on Zoom, so doesn't look too promising, guys. Okay, are we good? William, how are we doing? Everyone, here's to a great webinar. Here's to a great workshop. William actually writes the book for Kweller Preps Physics AP. So this is a very special moment that we're having right now, okay? And I'm gonna put the dog away and I'm gonna put myself away. And you're going to go on Spotlight, William. Bye, everyone. Bye-bye. Say
And do
bye,
I have
Goldie.
screen share
Bye,
enabled?
Goldie. Okay, everybody. Ready?
Do I have a screen share
Yeah,
enabled?
you should have everything. You can check right
And
now.
it says no. It
Yeah,
says
can you
host is,
check? Just
yeah.
confirm, okay?
All right, let's do it. It says still disabled.
Wait, what?
It says host
Oh,
disabled
really? Hold
participant
on.
screen sharing. Yep,
Wait. Hold on. Let me make
sure.
you co-host. One moment. Okay.
All right, let's try again. Ah, there we
And I'm
go.
gonna put you on Spotlight. Okay, I'm putting you on Spotlight. Hold on. Hold on. William. Replacing Spotlight. All right. Well, so much for my moment with the dog. Hello. William, you look very blue.
I should.
Okay, everyone. So I just want to let you know that I brought you the pro. So William is going to do an amazing review for the next 90 minutes, and I'm very excited. Okay, go right ahead, William. Thank you. Thank you for this moment. Thank you for your partnership and longevity, and I'm very excited. And students, this is going to be recorded, so you'll get to enjoy this after. Okay, go ahead, William. Thank you for doing this from California in a different time zone. All right, go right ahead, everyone.
All right. So, hello everybody. Feel free. I can check the chat at any point if you have questions. Yeah, this is meant to be interactive. Um, if you like, I have
Oh,
no
William,
problems. Yes,
can you just do chat with host or co-host? Can you do it's a chat setting. If you could just edit that on your ends. When you go to chat, it's just chat with host or co-host.
let's see if I click
So any
on chat.
questions? If the
Um,
three dots on the bottom.
all right, so the ellipses, let's see. They don't show up in the same spot for me. So, um,
I think
let's
we're
see.
okay. Everyone, you'll just message William if you have any questions, we'll get them.
All right, all right. Okay.
I'm
So in
going
any
back on.
event, let me give you the quickest take-home message that I can to introduce this. The most important thing you can do right now to prep for the AP Physics 1 exam is to get your hand on old AP Physics exams, the FRQs, and just do them. Not only do them blind, like don't refer to the answers, do them, and then grade your answers against the scoring criteria that they list on the AP College Board, on the official College Board. I cannot tell you, I wrote this book in particular because I was a teacher, I was a tutor, then a teacher. Now I'm kind of running my own educational business as well. And it was sad to me to see very capable people not do so well because they weren't instructed in the test properly. And this has been true for as long as I've been tutoring it. I just don't often see people do a good job. They'll teach you physics, but they won't necessarily teach you the AP Physics exam. So you need to learn the AP Physics exam. Some folks might have never even done a derivation that's completely based in symbols, right? You're used to solving problems where you plug in numbers, and then when you do a derivation based entirely in symbols, you might get lost. So this session is going to gradually progress in difficulty. I am going to start with something a little bit more familiar in kinematics, and then I'm going to go into a rotational problem. And these two problems come from my book specifically. And then I'm going to go into to two older problems that come from previous AP exams, um, just to kind of just to give you a nice assembly of different things that come from my book, from their source. But I wrote my problems to be very similar to the official ones. And yeah, let's go. So if y'all want, you can chat it to me, your answers as you go if you want to participate. Again, the best way to make use of this is to make it active. So let's get to this real quick. So I'll put you here. I can see me. Can't see any of you. That's fine. So again, there's a huge difference between active versus passive learning. Won't go into that. Don't really have time. But that just means, work. Don't just read through correct answers and understand them. Work. It is an entirely different thing to create it on your own. And this other bullet point of synthesis. Synthesis just refers to the fact that AP Physics exams are good at taking different concepts that come from different chapters. You have a chapter in kinematics, you have a chapter in forces, chapter in energy, and usually never the twain shall meet, right? But the AP exam is not like that. They're very good at cross-pollinating, and some students aren't used to that, so I want to give you a little bit of exposure to that too. And then, of course, I say less important is do content review of particular topics. So, your projectile motion, your forces, energy, simple harmonic motion, basics of waves, that's pretty much it. And I don't have to tell you all that the AP Physics 1 exam has the lowest pass rate of any exam. I think that's unfortunate. I don't think the exam's particularly hard. I just think it's not instructed correctly. And I think the College Board is out of touch with how it is instructed. So whatever, it is what it is, but you can change that. So here we go. I'm going to leave this on the screen. Again, this is a problem that comes from my book. But I'm just going to provide it here because I figured let's give you something you've had no ability to practice. So pause my screen and you're just going to do part A. It's going to start off simple. It's going to get more difficult. And I'll say 2 minutes. Oh, hold on. When I'm in full screen mode with Microsoft OneNote, it glitches out there we go. All right. 1 second. Okay. Part A. say like 30 more seconds. This one's simple. You just might have to hunt for the simplicity. All right, so let's go. So this is just a slight twist on a typical concept that the trick here is to recognize like, oh, I give you the final velocity that this rocket attains as it's firing horizontally off a cliff. Again, this is meant to be a slight deviation from a typical problem. Typically, your rockets are boosting straight up. This time I have the rocket boosting in the horizontal direction. So there's going to be a horizontal acceleration in addition to the vertical acceleration due to gravity. And this is meant to just, again, give you kind of a slightly different look. So calculate the average horizontal acceleration of the rocket during the first second. So then you would recognize, okay, this is a projectile. So what happens in the vertical direction is irrelevant to the horizontal direction, provided the rocket is still moving, right? So what's happening is, now in this case, typical projectile motion, you must recognize that your horizontal velocity is typically constant because there is no rocket boosters or deceleration or whatever, right? But you should be expected to know like, hey, if I accelerate an object in the horizontal direction, this is a trick you should know how to do. So in any event, it says calculate the average horizontal acceleration. So you would just say, all right, you go to one of those big, I call them the big three kinematics. Some people call them the big five. You don't need all five of them. Three is fine. So these are the three in the typical form they're given on the AP exam. And you would say, all right, I know the final velocity. I know the final velocity. They give that to me. That's 30. It starts at rest. So V final was 0, or V final was 30. V initial was 0. And they give you a time, 1 second, et cetera, plug in, get an acceleration of 30 meters per second squared. And again, if anybody has a quick question on that, you can just chat it over to me. I assume that one's pretty straightforward. They'll get more difficult as we go. All right. Part B. All right, another relatively straightforward kinematics problem. Calculate the height the rocket is at when the engines first stop firing. So again, you will see this trick of horizontal and vertical components are independent of one another. It will show up on your exam, guarantee. And they'll always try to disguise it in a new way you haven't seen prior. So calculate the height the rocket is at when the engines first stop firing. So we do know that the rocket accelerates to a final speed of 30 meters per second due to its acceleration of its rocket boosters, but this has no bearing on what happens in the vertical direction, right? We don't care about what's happening in the horizontal direction because those two components are independent of one another. So the height of the rocket when the engines first stop firing, well, all you say is, hey, I know it falls for 1 second, and it does not matter if an object falls straight down or it travels horizontally as it falls. They will cover the same vertical distance typical trick. So you're trying to figure out d final. And we could say, all right, for the sake of simplicity, I'll say it starts at 0. The initial vertical velocity is 0, so this term zeroes out. So I'm just figuring out d final equals, I'll say it starts at 0 plus 0. And for the purposes of the AP exam, by the way, although, as you probably well know, there's very few numerical calculations on the free response questions. So you're probably doing things in terms of entirely symbols, but in any event, 10 is fine. So 1/2 a t squared. And so I could just use 1/2 10 times 1 squared was the distance it was falling. And I mean, I could say, I also could begin with the initial height being at, well, let me show you how I'm going to do it. Like, I know it begins 13 meters off the ground, but I'll just show you real quick. So it is going to fall a distance of, obviously, fine, of 5. It fell 5 meters. So it began at a height of 13 meters, fell 5 meters. Thus, it is now at a height of 8 meters. I could have plugged in 13 right away. Doesn't matter, as long as you know where your relative positions are. Okay, so they're going to get a little bit harder as we go. Part C. All right, somebody sent me an answer. I appreciate that. So again, the trick here is, I'm trying to rehash the same trick over and over just to see if I could ever trip anybody up with it. But we know that the final velocity, the final horizontal velocity that it attains is 30 meters per second, right? We know that it'll accelerate for 1 second until it hits a final velocity of 30 meters per second. So that final velocity will, of course, be maintained. The horizontal velocity is going to be 30 meters per second the whole time through after it's done its acceleration phase. Now, for the vertical, you just have to recognize we do not care about what happens in the horizontal direction. Let's just treat it as an object that's being dropped from a height of 13 meters. And this time I'm going to go with the v final squared equals v naught squared plus 2ad. Again, 10 is fine for the purposes of the AP exam. And so this is going to be the square root of 260, which is going to be 13.1. However, you should indicate the direction. I would say it depends on the problem and how it's graded, but you either need to say 13 meters per second down, or you can call it negative. Either one is fine, right? You need some indication of the directionality of it. This is physics. So hope that was clear. It'll get slightly more complicated, I think now. Let's find out. D-ish. E is where I'm going to hit you with an AP style question. So part D, calculate the total horizontal distance the rocket travels before it hits the ground. And again, send your answers away. Appreciate it. Somebody sent me their answer. Thank you for that. It gives me an opportunity to see where folks are at. And if that person has any questions on what they sent, I'm absolutely open to respond to that while you wait. Actually, I take it back. This one's a decent kinematics problem. And I have seen one just like this on a prior AP exam. That's a correct answer, by the way, whoever who just sent it. Well, maybe you don't know who that is because multiple people could have just sent it. So I will say this. Here we go. I'll give one more minute for other folks. I rather like this problem. All right, folks, ready up? So calculate the total horizontal distance the rocket travels before it hits the ground. Well, this is another permutation of the horizontal versus vertical components thing. And you have to say, all right, well, there's actually something interesting going on with our rocket, right? It is accelerating for its first second of travel, but then thereafter it is traveling with a constant speed. So we have to break this. You have to calculate the two separate segments separately and then add those two distances together. So the trick of it is, and again, I'm just going to fly through this for the purposes of you all. I don't have time to show you my process. I don't think that's a good use of your time. So during segment one, we say, all right, it's accelerating at a constant, it has a constant acceleration, right? So I could figure out the distance it travels saying, hey, d final equals d initial plus v naught t, 1/2 at squared. And I say, all right, I know the acceleration is 30. There's the half, blah, blah, blah. It's doing it for a time of 1 second. And we get out that during segment one, when it is constantly accelerating, right? During its acceleration segment, it travels 15 meters. And then now we have a segment two, where it is traveling with the constant velocity. And we know what that velocity is, right? That's 30 meters per second. However, the thing we don't know is the time it is traveling for during segment two. So the first thing you need to do is say, all right, how do I find the total time that this rocket will take to hit the ground? Well, that's simple. Just calculate it as a projectile that falls straight down from a height of 30 meters. And you get, using one of the old kinematics equations, you get 1.6 seconds as the total time. Okay, lovely. Then you would say, all right, look, I know it travels for 1.6 seconds total. I know it travels for 1 second during the first segment. So the time it travels for during the second segment is simply 0.6 seconds. Then you say, all right, it's traveling for 30 meters per second for 0.6 seconds. Thus, it has traveled 18 meters. And now we just add these two distances together. You don't have to worry too much about sig figs, by the way. This is AP physics, not AP chemistry. In the grading criteria, I have never seen much concern for that. But again, there's not even that much data to go off of over the last 5 years because they rarely have a numerical calculation, which is unfortunate. So, but again, that's okay if you get used to it. Now, my favorite one of this, and for that person who's nailing these and sending them to me, thank you. I kind of hope this one trips you up. If it doesn't, hats off to you. We'll see. This is a variation of something I've seen on an old AP Physics exam, so I restated it. Oh, hold on. Let me do that again. Again, OneNote in full screen mode and Zoom do not get along. All right, I'll pause from here. Part E. And let me know if somebody can't read that. All right. Again, sorry if I can't give you enough time. My bigger concern is that I just kind of get you a sense of how these problems work, especially if you've never been exposed to them. And I'm not sure where you all are from. Through Francis, I've worked with kids at Stuyvesant, Bronx Academy of Science. I forget where else, but basically, I've worked with most of the schools you all are coming from, and I'm decently familiar with how these are taught. And I hope to fulfill a gap that might be there. So what I say first is when you're doing something like this, if you can, the best way, and you always should justify or rationalize your answer on the basis of some equation. They will even look for that. This is in their partial credit grading criteria. And you could speak with equations. You know what I mean? You could say, according to the kinematics equation, V final equals V naught plus AT, blah, blah, blah. And you could say, if we keep velocity the same and this and that, you should speak with equations. They want this. This is a great way to milk partial credit. So anywho, what I say with something like this is jot down relevant equations. Well, you're comparing, and think about the quantities you're trying to compare. This you have your three options here, but we have the issue of this one has a final velocity, which introduces another unknown. We don't want to deal with that. So I would say, all right, let's use this equation. And let's say they both drop to the ground. So that's cool. This thing zeroes out. They both begin at rest. So this thing zeroes out. Then I just do a simple rearrangement and I say, all right, we have distance is 1/2 AT squared, right? So that's what that equation simplifies to. Then I make a set of equations to represent what's going on Earth versus what's going on planet X. And say, okay, I got d naught equals 1/2 a, or acceleration of Earth, time of Earth. And then here's planet X, acceleration of X, time on planet X. And then now I make a simple substitution. I say, all right, the acceleration on planet X as it compares to planet Earth is 1/2 the acceleration as stated, right? So now I plug it in and I say, all right, when I compare these two, I say, here it is on Earth, here it is on planet X. Now, when they say, and this is a very common thing, you should look for this when they say, compare, blah, 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 or by what factor. When you think factor, you think divide one thing by another, just as a general principle, right? Never think subtract. Think, oh, I'm going to have this quantity and I divide it by that quantity. And when I perform this division and stuff cancels out, what remains, right? Okay, so that being said, we go back down to Nya. Now, we got these two, and I'm going to solve for time on both of these. So it's just a simple algebraic rearrangement. I solve for the time on both, and then now I'm going to divide the time on planet X compared to the time on Earth, right? I'm going to place Tx over Te. And here we are. The DOs cross out, the AEs cross out, and you're left with the square root of 4 over square root of 2. So that's you're going to end up with square root of 2, final answer. All good, by the way. That's all good. And again, I hope this helps, Rachel. I hope this helps you see like the setup, right? The setup, the division. The cool thing is if you lean heavily on the equations, it almost prevents you from making the mistakes. Like whenever I see these, I'm like, how do I express what they want me to do in equations first and then set it up? Now, next one's going to get a little bit harder. This one also comes from my book. This is my favorite problem I wrote. But first, the background. So Atwood's machine, it's a thing they love on the AP exam. They often, maybe not every year, but it's a thing that will show up quite often for the simple reason that it's a good way to see if you all know your physics without having you do very heavy mathematics, right? It's a procedure, and if you're good with the procedure, it won't trip you up. So I'm going to speak about it, just quick, simple review. If I have a mass on an inclined plane, on a pulley, and I let the thing fall, there's absolutely no counterweight on the other side, right? It will fall, it will accelerate at the speed of gravity, right? A equals G, as nothing's resisting it. If I place a mass, the same mass on the other side, well, now we got a tension upward equal to the mass downward. The acceleration will be 0 because upward force is equal to downward force. Now, if I place an unequal mass on the other side, well, now we're in a different situation. The acceleration will be less than gravity, right? We have a resisting force. And so I want to be clear, just some simple principles to review that this is here in bold. The tension must be greater than the weight of the small mass, but less than the large mass, which makes sense, right? The tension force upward must be less than big mg down because it is accelerating down. But on this side, the tension upward must be greater than little mg down because that side is accelerating upward. A simple way to look at it, by the way, is that this Atwood's machine, its manifestation is it just produces a tension that resists your motion of the other one. Now, what I do recommend you do, hopefully your teachers have taught you the same, you should create a system of equations to describe the two. And so I would say, all right, what's going on with the little mass? Well, you do your old F equals ma nonsense, right? and you pick a direction, and I will say that upward is positive for this system. And just to show it real quick, if upward is positive, then that means FT. So for this system, yeah, FT is positive minus MG, which is negative, equals MA. Now, last important thing, an easy place to mess this up. When you have an Atwood's machine, whether it's connected across a vertical pulley or an inclined plane pulley, that is a thing they've done. You should be able to handle something. My drawing is terrible. Never said it was any good. You should be able to handle an Atwood's machine on an inclined plane. You should be able to. You should know this. And I think it's in my book, but you can certainly find it on old AP exams. I'm pretty sure it's in my book. I'll check. So now you got this equation for the little mass. Now, last important detail: when you have an Atwood's machine, your directions must agree. If we have said upward is positive for this system, this connected system, downward must be positive. If the directions between your two systems do not agree, you will not get the problem right. So again, whatever direction, if I say, if upward is positive for this, that must mean that downward is positive for this. So now we create our equation for it using the convention we created. Big MG minus FT equals big M A. The F of T's will be the same because it's the same rope. And the acceleration will be the same because, of course, they have to be moving at the same rate. If one's accelerating faster than the other, you kind of got a problem, right? That means the rope is either elongating or shortening. This does not make sense. I mean, they could do that, but they can't do that. So then blah, blah, blah. You would just do a system of equations, plug one into the other, and you would derive this equation. But for the love of God, don't just memorize this classic Atwood's machine equation. You should be able to derive that. And I almost guarantee that the partial credit for one will revolve around showing the derivation. Like they will say, did the student show demonstration of equation for one system? 1 point. Did they do it for the other system? 1 point. Was the algebra decent? 1 point. And then finally, was the final answer correct? 1 point. So if you only memorize this, you're missing 3 of 4 points. And I often don't like how the AP exam is graded, but I think how they do partial credit is decent in general. Okay, now that's just the start of it. Now on to something far more awful. I love this problem. Okay. Here we go. This one is brutal. Take your time. I'll give folks like 5 minutes for this, and I will mute myself. Okay, sorry. Had to get the screen right. I'll say 2 more minutes. Probably not enough time, but um, at least it'll get you thinking in the right direction. All right. Ready? So this one I would say, um, this one I would say is a 5 out of 5 level derivation on the AP exam. Maybe a titch beyond what you might expect. I don't think so though. But again, maybe the more one of the more difficult derivations you would ever see on the AP exam. So that being said, when you perform a derivation, I say that here's a simple golden rule to go by for derivations. When you perform a derivation, you can only have the listed variables in your final answer and nothing else. So if it says they want the alpha, the angular acceleration in terms of big M, little m, r, and a, and any constants as appropriate, if you have anything other than those in there, you know you are not finished. But let me say one other thing so you're clear on this. You can only have the listed variables in your final answer, nothing else. But you don't need all of the listed variables. So never be afraid if you're like, oh shoot, I get my R's crossed out or I don't have an A in there. That's okay. So you just can never have anything other than the listed variables, but you don't have to have all the listed variables. This is an important golden rule for AP Physics derivations. All right, so what I say is the best approach with something like this is that what equations represent this? So you know there's going to be like an Atwood's machine here too, but there's clearly a torque, right? And so the only two torque equations are that you'd have is torque is equal to I alpha, and torque is also equal to the force applied perpendicular times the distance, right? Those are your two main torque equations, I alpha and force perpendicular times distance. But of course, you could set these two equal. So you got I alpha is equal to force times distance. I'll just call it that. Now, okay, look, we've got our alpha there. But, we got this I needs to go, this F needs to go, and this D needs to go because none of these are listed. So that's okay. One of the things I recommend when you do a derivation is you jot down general equations to describe the situation, and then you just start plugging in other equations with wild abandon and hope things cross out. And I know that sounds a little bit silly, but it's actually the right strategy. So you say, all right, well, what is the force being applied here? Well, we know that the force is coming from the big mass, and basically it's the tension. Well, it's the tension in the rope which is going to accelerate this cylinder, right? It's going to accelerate it rotationally. So we can make an Atwood's machine equation for it. We'd say, all right, net force is equal to ma. I'm going to call downward positive because that's going to make my life easier, because I'll call this tension positive, right? Okay. Now, F net equals ma. So what's acting in our positive direction? Big mg. What's acting against us? F of t. And that's equal to ma. Now you would say, well, this is nice. If I rearrange, I've got tension is equal to mg minus ma, right? And this is acceptable. I can use m here. So we're getting there. So, okay, mg minus ma equals f of t. So this lot gets plugged in right here. And so now we're here. But we're getting there, but we have this problem. Remember, D is not allowed and I is not allowed. But we can get rid of these. Again, one level at a time. Just start throwing equations that fit the scenario with wild abandon. Well, the distance, remember, torque is force times distance to the pivot. Well, the distance to the pivot here's the pivot. It's a rotating cylinder. The distance to the pivot is the radius. So we would just plug in R for D, right? All right, we're almost there, actually. Now, last thing, you will never have to know these, but they might give them to you and they say, all right, you do not have to know the rotational inertia for any object, but you should be expected to know how to work with it. And they say, here it is. The rotational inertia for a cylinder spun about its central axis is this. I is 1/2 mr squared, right? Okay, well, now if I plug that in, you're going to see stuff finally disappear. So I plug in 1/2 mr squared. No, I'll leave it in parentheses. I teach many subjects, math, calculus, etc., being amongst them. I recommend use parentheses when you plug in. It just helps avoid silly mistakes. So I plugged it in, and now you can say, all right, I got an r squared over here and an r over here, so this goes away. Bring the 2 over, bring the mr on the bottom, and here she is, final answer. Any questions on that? I know that one's rather brutal, but it is a good example of a cross-pollination of different techniques, equations, concepts in one problem, a thing you should get used to, which is unfortunately not typically taught in most classes, right? You have your kinematics test, your forces test, your energy test, but maybe not a test that incorporates. Yes, this is the only right form of the answer. This would be the only acceptable answer, for sure, because it's the only one that demonstrates. It's the only one that demonstrates full knowledge of the situation. You know, for instance, it demonstrates that I know that the rotational distance to the pivot is r. I know that the setup is correct. The student has identified, like the partial credit might be, did the student set the 2 torque equations equal to one another? 1 point. Did the student use an Atwood's machine setup to figure out where the tension comes from? 1 point. Did the student perform adequate substitutions, etc., right? But this would be the only correct answer. All right, now continuing. This is another very AP style question. And I will pause for you. And let me know if y'all can't see that. Okay, I think that was enough time for this one. So, very common thing on the AP exam as well, where the state of the system will transition, and then and then also to create a graph that shows what happens during that transition, and they'll call it like time T1 or T naught, etc. But, so we have this rope is wrapped around the cylinder. It is going to accelerate the cylinder rotationally for a period of time, and then the rope detaches from it, and it is frictionless, etc. So, what will happen? Well, let's break this down, and I'll break it down into two phases. You don't really need you don't need to use equations. You should understand the equations are relevant here. But basically, during the first segment, the angular acceleration is constant, right? The mass is pulling the thing down, spinning the cylinder up, constant acceleration up until the point where the rope releases, which I'll cover in a second. And similarly, a constant acceleration means a constant slope in the velocity, right? This is basic physics or your calc, right? If you have a constant acceleration or constant acceleration, that means a constant slope on velocity. Okay, and then the rope detaches at time t1. So what happens? So it is okay to show this is a discontinuity, but this is AP physics. That's fine. You don't have to show it like rounded out to this to this. AP physics is always meant to be very simplified, right? No air resistance, et cetera, et cetera. So you could say, all right, it's a constant acceleration until the moment the rope detaches, then the acceleration drops to zero. So those are your two segments. Constant acceleration drops to zero, whereas the angular velocity speeds up, speeds up, speeds up, and the moment the rope detaches, well, it's just going to keep spinning with the same angular velocity. Okie dokie. Now, another very, very AP style detour. Well, let's just take a look at it. Hope I wasn't muted prior. I don't know. I don't think I was. But yeah, here, just take a look at this. And 5 minutes. Okay, I'm gonna go after this in long, like showing you it in long form with equations. Although it's not necessary, right? It says it can contain diagrams and/or equations, but it's not necessary. So here's what happens, right? We have a cylinder, it was spinning, and then I drop another cylinder on it and it welds itself to it. Now the two spin together. Now they have the same mass, but the problem is that the second cylinder has twice the radius of the initial cylinder. So what would happen? Well, first of all, this is the thing they would look for. They would say, is the student justifying it in terms of conservation of angular momentum. So you would say, you don't have to show the equation explicitly, but you do have to use the rationale. You say, all right, according to the conservation of angular momentum, so we know angular momentum initial equals angular momentum final. And by the way, just a fun thing, this comes from your Giancoli textbook, right? But you know, a neutron star, which is, you know, a condensed version of a regular star, ends up spinning with a velocity of, or an angular velocity of 2,000 revolutions per second. Isn't that crazy? Something the mass of the sun spinning 2,000 times a second. That's crazy. Okay, so in any event, you got initial angular momentum equals final angular momentum. So you'd say, all right, the initial system is just I omega, but the final system contains two i's, right? And it's omega final, right? It's got the momentum of the first cylinder and the second cylinder added to it, right? So no big deal. Now for the first cylinder, it's just 1/2 mr squared. But for the second cylinder, well, the second cylinder is, you know, 1/2 mr squared, but that second r, which I'm labeling big R, is twice little r. So I'd plug that in. And so after just rearranging and solving, here's the first cylinder, here's the second cylinder. Now I'd plug those both in. I1 omega 1 equals blah, blah, blah. I plug everything in here. Boom, boom, boom. Do a bunch of fun algebra. And we find that omega final is 1/5 of omega initial. So again, if you showed it like this, you'd get full credit. Or you could speak with it like, you could just use words and you say, all right, according to the law of conservation of angular momentum, angular momentum must be conserved. That'd be a point. The initial angular momentum of the system is just this thing, right? I cylinder plus omega 1. If the second cylinder added was simply a cylinder with the exact same rotational inertia, the total rotational inertia would be double, meaning that omega 2 must be half of omega 1. That makes sense. At double the mass, radius stays the same, it would be half. However, the second cylinder has the same mass, but twice the radius of the original cylinder. This means that the rotational inertia of the final system would be more than double because the rotational inertia of the cylinder is dependent on the square of the radius. This means that omega 2 must be less than 1/2 omega 1. Absolutely, absolutely, Rachel. In fact, speak with equations. You could say, according to blah, 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 according to this equation here, I prefer you do that because that saves you time. Speak with equations, they like it. And I'm sorry if no one's explained this to you. It drives me nuts that this is the case. I've been doing this for a while. I know it's not typical, but no, they're expecting you to almost speak with equations. They like it because this is how physicists, this is how physicists, you know, I mean, they speak with equations. This is how you write your papers. You speak with equations. Okay, now, shifting forms here. I think we have time for one more. Just take about a half hour apiece. Maybe we could get through two more. Everything I gave you all. Let's take a look at this one. This is a 2017 experiment one. Oh, to answer a question here, if we just show work in that process and don't have that paragraph, I'm pretty sure for something like this, because they have given you the qualifier in clear paragraph length response, they're expecting you to use, you can get away with entirely words, you cannot get away with entirely equations, but you should do a hybrid of the two. You know, like whatever the problem is asking you to do it that way. Do you know what I mean? Like fit your answer to their mold. It will make them happy. I guarantee it. And you'll get more credit for it. Let me say this real briefly, right? Like these tests are graded by individuals and they have a stack of these on their desk. How do you think they're going to grade them? Are they going to read each answer in great detail and see something that is a very eloquent explanation? They do not care. What they care about is, did the student do this? 1 point. Did the student do this? 1 point. Did the student do this? 1 point. Is the final answer correct? 1 point. This is how you have to grade. Right? Yeah, no problem. I just want to get you all used to this because you might not be used to that. And I graded, I taught a college class prior to where there was 300 people in it. This is how you have to do it. You know, if I'm grading 300 tests, there's no way I could look at them in detail. It's just not how it works. So what I do is I flip through the exams and I look at problem one. I grade them all at once, all 300 of them. I'm like, all right, did the student say this, this, and this? Yay, next one, boom. Next page, 299 to go, 298 to go. This is how it has to be done, unfortunately. There's nothing wrong with it. It just can just understand the system you're trying to master. All right, anywho, part A, careful with this, and I'll explain why in a second. I'm going to do that again. Okay, again, I don't think this was enough time, but I'll highlight many important things with this problem. So draw a diagram of the experiment setup of the board and the block, blah, blah, blah. Okay. So again, if you were to look at my book or you were to look at the answers provided by the official AP exam, I always say, do your answer first, then refer to the grading criteria, because you ever hear the adage like professional poker players do not remember their great wins, but they recall their greatest losses with striking detail? The same logic applies here. If you do a thing and you make a mistake on it, and then you go back and correct it, that will stick into your brain far more, right? When we're wrong, it sticks better. I think it's a evolutionary trait, which is a good thing. So do it, be wrong, let that stick and adjust. That's a good thing. So in any event, and then the partial credit for this is going to drive you nuts. So in any event, recall static friction force is the force that prevents two surfaces from sliding past one another, blah, blah, blah. So let me just skip to the answer because I think this one is decently simple, but you might not have articulated everything they wanted. So we say, all right, to determine the force of coefficient of static friction, attach the force gauge to the side of the block and use the gauge to pull the block parallel to the board, gradually increasing the force until the block breaks free from rest. This is the value for Fs. Repeat multiple times and take an average to increase accuracy. Now, next part. Now hang the block from the force gauge to obtain its weight in newtons. This value is equal to the value for Fn. You will need these two values later to derive μs. So many important things that I do not like about this problem. Notice part A, you almost might be tempted to start deriving the equation, but they don't want you to, right? You almost have to derive, in some sense, you might have to derive the equation in order to see everything you need to do in your experiment, right? If you inadvertently derive your equation in part A, you have to do that again for part B. Never say, see part A. You will not get credit for it. Avoid that mistake. And that's the thing I had to learn too. So in any event, we're getting things set up. Again, you might want to do parts A and B together because B will help guide you as to what you need to do for part A. So, but look at this. This is the thing that's a little bit unfortunate. I want you all to be used to this because this is the game you have to play. Look at this. And these are the actual point criteria from the College Board. 1, 2, 3, 4, 5, 6. This is worth 6 points for this silly answer. Versus that derivation we did earlier, this big awful thing, this is probably worth 4 points. Just so you know. It's silly, but that's how they grade. So one of my points with this is like, bide your time carefully, watch how you use your time for partial credit, and read it, and it says, oh, now it doesn't give you the individual breakdown of each part, but notice this is worth 12 points, so keep that in mind. All right, anywho, so some hacks for you all. Drawing a diagram that demonstrates a procedure, okay, 1 point. Describing the procedure, 1 point. Here's a point for being clear and concise. All right, 1 point there. Indicating all quantities that need to be measured. Mentioning the proper equipment. And here's a simple hack, mentioning a way to reduce experimental error. The stupidest, simplest hack in the world for partial credit is how do you reduce experimental error? Repeat multiple times and take an average. 9 times out of 10, that will get you a point. Just say, all right, I'll do the trial multiple times, take an average. Maybe, however, maybe you'll have to say repeat which part of it, if that makes sense. Okay, moving on. All right, part B. Derive an equation for the coefficient of static friction. This one shouldn't take you too long. I'll pause. Oh, I know what I'll do first. I'll do that. Now I pause. Okay, this is just a very incredibly simple derivation. And as I said to somebody, yeah, as I said, it absolutely causes overthinking. So this is another thing I am happy to give you all here. Do you know what I mean? Like that you'll have a brutal derivation like the one we did. And then it'll have another derivation be like, wait, is that what they want? It is. Again, problems with it for sure. Problems with it for sure, but whatever. We're not here for politics, right? So derive an equation. So all you have to do is you say, you know, the force of static friction is equal to mu s times Fn, and then you literally just rearrange Fs over Fn is mu s. And then they do want to comment though, let's go back to it. Derive an equation, well, not really, but derive an equation, blah, blah, blah. So here's the points, watch how they break down. The statement of, again, milk partial credit, y'all. The statement of show the use of F equals MA. That's a point, right? Noting a procedure that can indicate Fn, fine. Using algebra logic, blah, blah, blah. Okay. Part C. This one's kind of cool, I think. We'll see. It's been a bit. Okay, this one's a bit tricky. It's a bit tricky because you might be of dual minds in that, like, well, am I expected to bring outside physics knowledge into this discussion? And the answer is absolutely. And you should know that the coefficient of static friction is always greater than the coefficient of kinetic friction. And that's right. And the answer that someone gave me is 100% correct. You have to account for the outlier. There's a clear outlier in the positive deviation for kinetic and a clear outlier in the negative deviation. Student 5, not on their A game at all, right? Student 5's data is not to be trusted. That's the important message here. But in any event, you would say, how would you frame your answer? You would say, all right, your outside physics knowledge, mu s is always greater than mu k. And by the way, if that weren't the case, do you realize all objects would be sliding if mu s wasn't greater than mu k? If you think about it, that makes sense. Objects would be spontaneously sliding. That's kind of a problem. So observing the data, it appears that lab group 5 made significant errors in their experiments. If you remove their data, the averages would be more accurate, et cetera, et cetera. Part D. Hope you all are hope you all are deriving something from this. And look at this. You can see a little bit where I got the inspiration for my problem from. This is straight up outside knowledge. I won't give much. I won't give too much time for this because you shouldn't need it. Okay, ready? So you should know. Let's just go to it in case. Nah, I'll just kind of no. I'll fine. I'll copy and paste it just so you all have it because I'll give you this document after too if you like. But you should recognize this is a thing discussed and it should be discussed in your physics class. That coefficient of friction is an intrinsic property between two materials, right? It is not dependent on the weight. It is not dependent on the surface area of contact, which is pretty interesting. That you could take like a giant wood block, like a giant, very tall cylinder of wood, or now maybe a giant rectangular prism of wood, and if you slid it across the ground like this, it'd take the same amount of force as if you just dropped the thing on its face and then slid it. It would be approximately the same, which is true in only the ideal sense. But in any event, the coefficient of static friction will not change because it is an intrinsic property between materials. It is not affected by the increase in weight. And if you ever do your derivations, you know that m's cross out in these situations, right? So I want to be clear that in my book, I rewrote it. I read carefully the answers that came from the AP College Board, and I tried to flush them out and get in their minds a little bit better, and then state it a little differently, because what's the point if I'm doing exactly what's on the website? That's a waste of time. So in any event, all right, we could get in a little bit of one more. We got 8 minutes. Let's do this. So let me go to our last one. Okay, another one, another quick derivation. Copy. I'm going to throw it here in my annotated. If y'all don't use OneNote, you should. It is a lovely but very, very buggy program. Now, let me say one more thing real quick. Whenever you see an I and an II together, you almost want to do both of them together and then break up your answer for each part, if that makes sense, right? I might do both of these answers at once and then just make sure that, I have the answer, the bit of the answer that belongs in this one here and the bit of the answer that belongs in this one here. Why? Well, very similar to the problem right here. Like when you're doing the diagramming the experiment, when you're coming up with the experimental setup, you almost need to derive the equation, or for part B rather, you almost need to derive the equation to do the experimental setup, if that makes sense. That's the thing that's going to happen. So I just want you to be prepared for this. So this way, when you see it, you won't be blindsided. All right, we could get at least these done. This is what I would call a decently fair derivation. And wait till you see its partial credit. It's crazy. Okay, I will just go over the answer for part I first. Again, in this case, you should, but I'm telling you this prior just in case. In this case, you should do I and I separately, but I don't recommend that as a general strategy because, as I said prior, these are often connected. In this case, they're not. So they're completely separate situations. So assuming the disk begins at rest, determine the expression for final speed of the disk relative to the surface. So this is impulse momentum, straight up, nothing beyond that. So remember, impulse is equal to change in momentum, but it is also equal to force over time. Yes, you could set those two equations equal to one another. And don't even worry about this, but you basically just set them equal and solve. This is just making the point that, T final, delta T is T final minus T initial, but just say it starts at 0. So delta T is just T final, et cetera, et cetera. There you go. And again, silly, this is worth 1 point. It's ludicrous. Ludicrous. Get used to it. Okay. Last one. I. And then we'll call it. All right, last one, kids. Assuming there's negligible friction between the student's shoes and the surface. Oh, I just crashed pretty hard. Good, we're not gone though. All my screens just blacked out and they're reset, but I'm here. All right, assume there's a negligible friction between the student's shoes and the surface after time t final. Student slides speed vs. So you just have to recognize that, oh, this is an inelastic collision in reverse, which is also known as an explosion. You set it up, you got two objects that split into individual objects with different masses. Yes, you would need to show work for conservation of momentum, by the way, because again, this one is always be aware of the particular situation you're being asked. Because it says derive an equation, here you would not need any words of explanation, just so you know. When they say derive an equation, they want boom, 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 steps, right? And again, the partial credit grading criteria all over the darn place. You would show this conservation of momentum and inelastic collision in reverse, one thing splitting into two. But because the initial momentum is 0, the whole left side zeroes out. So the two things on the right side can be set equal to one another. And now you make a proportion. And here it is. And the silliness of partial credit, 2 points. Who could say? It's really ambiguous how they assign partial credit, I think. I have, to be fair, I haven't looked at the 2022 exams, but I have done, without exaggeration, 30 years of these exams. I mean, I haven't been doing this for 30 years, not that old, but I've done every exam from 2022 backwards, every single one I could get my hands on. There is no continuity in how they assign partial credit, I promise you that. So that's okay. Just be ready to over answer everything, right? That's the general rule. The take home message is show all your work, show the equations you're generating, um, show your steps. Because if you just get the final answer correct, that is often not how you're going to get it, get your points, right? You only need to get a 60% on this to either get a 3 or a 5. I actually forget which it is. I think it's to get a 5. You only need a 60% overall to get a 5, which is crazy. So if you're missing a lot of things here and there, no worries, you might still get a 5. And most of the kids that I coach through this get 4s or 5s. I mean, provided you do the additional work. To your question the question was asked, do you get points deducted for adding superfluous info? Rarely, although I have seen that show up. So a test taker or test grader is usually aware of when a student is trying to give you 2 different options so that you select the correct one. Do you know what I'm saying? But often, if you give a very long answer and it's got superfluous info, usually it's to your advantage because sometimes they might want that. There is a question from, I believe it's a 2015 exam, where you have to state the most obvious things to get partial credit. When describing an experiment, can you say to collect this data but not end up using it in a later part? Yeah, yeah. Although one of the things that the AP exam is decent about is usually one part leads you to the next, right? They're usually kind of trying to walk you through the full process. That makes sense. And that's about it. We're at time. If you all want to check, I have, I'm pretty sure Frances has she's got an old recording of this one. I might have done some of the things the same, some of the things different. I don't know. There's also my YouTube channel. It's at The Thinker Teacher. I did a solution, step-by-step solution on there as well. And if you ever want to check that out too, that'd be great because I'm building a whole channel to teach like STEM robotics at home. So like, for instance, we 3D model and program a fun little Nerf turret here. So, and things like that. I teach the fundamentals of game design, robotics, etc. But there's also some stuff on physics. That's my older stuff though, from helping a student through it. Any questions, kids? I don't think Frances is here. I'll take a couple more questions. I don't see her. Anything quick? You guys fire it off. Like, I'll give you a bonus time. Fire it off in the chat and I'll see what I can do for you. Well, I'll hang like 5 or 10 more minutes and wait for a question. But again, just get on. I'm not recommending my book, just because it benefits me, but I wrote it because I thought it was very useful. I've been teaching for a very long time in different levels. I've taught at grade school, I've taught at high school, I've taught at college. And I do not like the prep. I do not like the prep in most of those books. They're basically another textbook that's teaching you physics. You don't need to really learn physics. You've had a physics course. You need to learn the exam. So my book I would recommend, or failing that, just do old AP exams. Do free response questions. That is the best use of your time. Something else to that point, if you look up on the College Board website and you do the other questions, their practice questions that they make available, they're not the same. They're written by completely different people. I don't even think they're good prep. So like, it gets you used to doing a particular type of problem. I think they're terrible. They're not good prep. Do old AP exams. That's your best bet. That's true with any test. Just find old exams and do them. I don't care if it's SAT, ACT. In my case, I had to take the MCAT since I went to medical school as well. I just did old MCATs. That's it. Best use of your time. That's a good question. Let me think about that. When you're doing a free body diagram, sometimes, I know this isn't exactly going to answer your question. When you're doing your free body diagrams, just be aware that sometimes you'll have to draw your arrows to scale. But let me look at some old exams. Let's show you some. Here. So here they all are. I told you I got them all. Sorry, 30 years was an exaggeration, back to 1999. So let's look up at 2021. But often I would say in general, like, so when you're doing a free body diagram, those should be done to scale, but this probably isn't. This is a very hard derivation. This is a good one to do. So this is from 2021. This is one of the few times where you're incorporating a theta. In fact, the only time I've recalled seeing a theta being used. So you have to use a kinematics and conservation of energy to solve this one. So this one I would not say is drawn to scale. There you go. They even say figure not drawn to scale. Nothing there. No, not typically, I'll say in general, no. And I could look up a couple more. I'll look up something else while you all ask questions. Of course, there's no exam in 2020 because COVID. Another good one. I like this question. This is the 2019 question 3, conservation of energy. And it's not hard. It's just formatting your answer to get the credit. And if you have not practiced, if you have not done, and I would say your minimum is you should do 5 free response questions or 5 full tests worth of free response questions at the minimum prior to taking your exam, at the minimum. Anything else? I'll wait 2 more minutes. But I get you on using to scale to help you out. It's a good strategy. It's just not a safe one. When I do my own diagrams, I try to do things to scale because it just helps me think. Helps me think. All right, I'll wait 1 more minute, then I'm taking off. Well, the direction of the arrow is okay. The magnitude of it, that I would not know. But I'll have to see which one you're referring to, right? I've gotten MCQs wrong because I trust the direction of an arrow. Do you remember which question that is? If not, no worries. I don't doubt you. I don't doubt you at all. I just don't know which one you're referring to. But yeah, get in those questions. That's it. Number 1 thing. Like 2 carts with arrows pointed in the same direction. Ah. Huh. Was that the last year's? Was that the 2022 exam? All right, y'all. Oh, a random MCQ practice. Well, I wonder if, oh well. All right, y'all. So again, try my book. Might be helpful, but failing that, just do old exams. That's it. Your best bet. Don't even worry about the if you're ready for the free response questions, you're ready for anything. I'll just put it like that. All right. Bye-bye, y'all.